Okay, good afternoon, everybody. Welcome to everybody online as well. It's a pleasure to introduce Anton Kutyrev. Anton joined us very recently in the school. He has an undergraduate degree from St. Petersburg University, a PhD from Kamchatka in the east of Russia, and then completed a 12-month Fulbright visiting scholarship at the University of Oregon in the US. And then completed a 2-year postdoctoral position at the University of Cardiff, working with Wolf Mayer on magmatic sulfide deposits. And now he's here at Wits, working on the Bushveld complex. So Anton's going to all corners of the globe and lots of experience and knowledge about PGE deposits. So I'll hand over to you, Anton.
Yeah, thank you, Ben.
Thank you.
Thank you. Good afternoon, everybody. So just a few words. What I'm talking about is Alaskan-type complexes. Some of you could have heard about them, some not. This is another type of ultramafic complexes. In some senses, similar to what we have here, like in sense of Bushveld, Itkomst, or in some senses, very different. So I will try to tell you what the talk I will present you today will be parts of my PhD work with some of parts of general knowledge about this type. So I want to just, my goal is to a little bit and widen the horizon, because this is something which in South Africa is not represented. I know, like, this is a unique country with fantastic geology, but this is not what you find here. And I hope it might be useful for you to make your, I would say, view on geology and ultramafic rocks a bit wider. So, only the mouses. No. Okay. So, a little plan. What are the Ural-Alaskan-Type complexes? A little bit about Alaskan and Anton-Type complexes, mineralization types which are hosted in these complexes, detailed description of some complexes in Kamchatka from my PhD work, discussion of the reasons of zone structure per parental melt, volcanic phases related to these ultramafic magmatic complexes, origin of platinum mineralization, and some perspectives. So definition. Now, first, we have several types of ultramafic complexes. The one which you're probably most familiar is late intrusions, and of course the biggest, the most known, the most economically valuable example is Bushveld complex. Second type are phthalites, alpine type iridotites, all different types of upper mantle, lower crustal rocks which are exposed in the places where deep horizons of the crust upper mantle are exposed on the surface, like in island arc terrains, in collision zones. They also have chromatites. Actually, this is probably the largest chromatite body in the world. It's tens of meters, in Kazakhstan, but they are poor in PGE. And the third type is Alaskan-type intrusions. You can see they are very small, so Bushveld and phthalites, they can be tens and hundreds of kilometers. Alaska-type intrusions are few kilometers. They're small. They have very characteristic zonal structure. You can see here, central part is dunites and less magnesian rocks towards the outer parts, and they have chromatites. You see, I've forgotten to put scale here, but actually the width of this chromatite is just 2 centimeters. So normally very small chromatites, which nevertheless have significant platinum mineralization. And an interesting thing which you might know, the first platinum before discovery of UG layers here in Merensky, which humanity knew, was derived from Alaskan-type intrusions. This is the source for placer platinum, which was mined in Americas by Native Americans before colonization by Columbus. And this is similar complexes in Russia were the main source of platinum before the discovery of UG2 and Merensky. Apparently, when they were discovered, the significance of these complexes went down. So definition, like how can we derive them? How can we distinguish from other complexes? First, size and structure. They're relatively small. They have zonal structure, and they have highly tectonized context between units in country rocks. So you don't have these parallel flat layering like you have in Bushveld. Second thing, composition. Dunite, rhyolite, and pyroxenite in gabbro. You never have orthopyroxene and orthopyroxene rich rocks. You have a lot of planopyroxenites. I will tell it's most likely related to hydrous nature of magnets, which separates its plagiar clays. And in few complexes, alkaline rocks and even carbonatites are present. Here you can see some typical examples. Sorry, it's not very well visible, but you can see it's in Russia, in Alaska, in Siberia. you can see the small rounded circular complexes with zonal structure. Geological settings. It is mostly island-type terrains for Alaskan-type intrusions and platforms for Aldan type. Aldan type is almost the same, but with more alkaline rocks. And mineralization. Subeconomic load, e.g. chromium, platinum places. So this subeconomic load mineralization gives birth to large places, sometimes tens, or in one case, more than 100 of tons of platinum. Titanium, vanadium, iron mineralization. Generally, almost no sulfide and sulfide-related deposits in ultramafic rocks, but in some exceptional cases, you may have copper, nickel, palladium sulfide mineralization in gabbroic and Mons Gabbro, most evolved rocks from these complexes. Distribution. So all confirmed Alaskan-type complexes are Phanerozoic, so they are young. There are several cases, mostly in China, when people claim that they found some Proterozoic or even Archean Alaskan-type intrusions, but they all are quite controversial. Not only China, yes, there is one in Saudi Arabia, no, not Saudi, in Ethiopia, one pretty old, but all confirmed Phanerozoic. These are two examples. This is Ural platinum belt. Up to 1920s, it was the source of 99% of platinum for humanity, these small black bodies. This is island arc terrain, approximately 380 million years old. And this is example where I worked in Kamchatka. You also see all this green thing is late Cretaceous island arc terrain, intra-oceanic arc. And now exposed are these complexes with age approximately 70 million years old. So I told you a couple of words about Aldan-type complexes. Sometimes people don't distinguish them as separate type because they are very similar. They have exactly the same types of mineralization. They have exactly the same zonal structure, exactly the same places. This is one of the most fantastic examples. You can even find it in Google Maps. This is the circular complex. The central part is zonal ultramafic intrusion. And this is metamorphosed metasedimentary rocks, which were, how to say, uplifted when the intrusion was raised up. So unlike Alaskan-type intrusions, Aldan-type is located on platforms. And it has much bigger proportion of alkaline rocks, sometimes even some carbonatites. In this case, the central part is mostly dunitic with small chromitite veins. And from people who've been there, I know that normally it takes 3-4 hours to find visible platinum in the sample, in the load sample. Only places were mined, so you can see here a placer of Kandur and Ural-Galan River. More than 120 tons of platinum were extracted in like 20 years. So this is a huge sum of money, like ton of platinum. How much is it like? $100 million. I don't remember the prices currently, but so mineral resources. As I said, platinum from places. This is one of the largest nuggets ever found. 6.2 kilograms of platinum. It's found now in Vienna, in Austria, but it was found in Russia. In Moscow and Kremlin, you can find the largest nuggets up to 9 kilograms. Platinum was so abundant then that even platinum coins were minted and actually used. As I know, it's the only case in history. This is an example of one placer in Kamchatka. It was discovered in 1992, and you see the production of platinum per year. As I said, the first platinum known to humanity comes from these complexes. Another type is iron, titanium, vanadium. It's maybe quite surprising because normally, you know, like when you plot trace elements for island arc rocks, they're generally not too rich in titanium and vanadium, especially in titanium. But here you can see this example, Kachkanar deposit in Urals. This is the pyroxenitic part of this complex, so you don't have donite ultramafics here in the pyroxenitic part. And the blue here is pyroxenite with titanium magnetite. This is quite an interesting story about why you need to consult with people who understand the geology. In 1990s, a guy illegally built a Buddhist monastery on top of the probably biggest titanium deposit in Russia, which wasn't a good idea. So he tried to find it legally, but in 2022, it was demolished. This monastery was located right here. So they currently finished mining here. This is this quarry and going to mine this part. Copper, palladium, and gold, as I said, normally not to reach, but you have some disseminated low sulfide ores into the peroxenitic and gabbroic parts. Okay, let's come to one example. This is a complex from my PhD. It's located very in the middle of nowhere. So this place, you need to take like 3 hours by plane from Ural-Alaskan-Type, then like 3 or 4 hours by helicopter, completely uninhabited. The closest village was 100 kilometers from there, so no roads, no people, and perfect zonal structure and fantastic exposure. Just relations which are quite interesting from my point of view. You can see here some pyroxenites and some dunites, with dunites being apparently quite secondary ones. So this is illustration of this model when melt is infiltrating from either marsh or already solidified rock, and you have the residual which forms something vein-like. So origin of zonal structure. This is a big problem because like why it is zonal? You can explain layering like you have in bushveld. And some people try to explain zonal structure. As I mentioned, you have several layers, then you bend them, cut, you will have zonal structure. But it doesn't work like this too well enough because you don't have such type of layering when you investigate well-exposed complexes. Geophysicists made some works pretty impressive in British Columbia. This is, for example, how 3 complexes look in depth. So this is the system with the root and several funnel-like bodies. One of the explanations is that basically you have flow differentiation in this tube-like magmatic channel where the heavy crystals were pushed to the center, and this crystallizes from center to the bottom parts. That's why you have dunites and more evolved rocks closer to the walls. It sounds counterintuitive, but some analog experiments showed that this process is possible. But there is also another idea. Okay, let's summarize. Yeah, this is also another idea which explains these complexes as results of diacharism. So remember when I showed you a picture of contour complex when uplifted metamorphic rocks, one of the ideas is that these metamorphic rocks are squeezed to the surface, and the zonal structure is explained in a completely different way. Dunites are considered part of upper mantle or lower crust, and surrounding rocks are considered the products of reaction with gabbroic melts, which form during this process. I personally prefer another type of model. Coming back to zonal structure, so here I plotted 2 parts of layered complexes. First of Ural-Järvi from Finland, and another one is Wits from South Africa. You may see how similar they are in their structure. So they have 400 meters of ultramafic rocks, then transition with dunites or with lights and pyroxenites, then gabbros. These intrusions, at least in these sections, are like twins, with one different. Wits is mineralized, but probably because it's South Africa and things should be mineralized here. Like this one is barren in Finland. But if you stretch your imagination and look, remember I told you about zonal structure for Alaskan-type intrusions. You basically have the same thing. Just if you will imagine that you have a flat thing with such type of structure, you bend it and cut, you will get a zonal structure. And what is interesting, Wits is widely explained as conduit for melts, as Ural-Järvi. And this makes sense because Alaskan-type intrusions in the prevalent models also explained as conduit system beneath arc volcanoes. So I think this is just an interesting story about how completely different complexes from different settings may be compared. So yeah, alternative ideas. I was writing a bit too fast. Actually, I have slides about translithospheric diaparism. So these are the schemes which describe these ideas about peridotite, semi-molten, marshy, and molten being brought through the lithosphere up to the surface, and they explain in this fashion this uplift of the rock surrounding contour. So what is arguments for this model? Many complexes have metamorphic aureole, sometimes 100 meters, which is interpreted as a result of interaction between solid ductile dunite and contour rocks. Some textural resemblance between Alaskan-type intrusions, ultramafic rocks, and mantle-derived phthalitic peridotites. I showed you dunite veins and pyroxenites. podiform chromatites. Gabbro is often detached from peridiotites and form large separate intrusions. But contra, like in some regions, for example, where I worked, all these things are absent. You don't have metamorphic Urals, you don't have uplifted rocks. Dunites are very different from mantle perioditites, as we know in analysis sense of calcium in nickel and olivine and PGE patterns. So actually, I don't think we have any reason to think that these dunites are from mantle. So primary melt. There are several theories about composition of the parental melt for these arc intrusions. Polyisic melt, ankeramitic, this is, most people are not aware about this term, but this is specific high calcium/aluminum ratio melts, and picritic, normally from shishanitic series. So common denominator, the melt is hydrous and oxidized because we see it. This is what we expect for arc settings, and this is what we see from, for example, lack of orthopyroxene and the presence of clinopyroxenides because high water content suppresses both plagioclase and OPX. And oxidized higher and prominent spinels, little sulfides, especially in ultramafic rocks, virtually no sulfides. So we conducted field work in 2021 in Valaginsky volcanic, in Valaginsky range, in Turmeric range. So this is here. Here colors are different. So the blue is this 70 million years old arc terrain. And here picritic series are exposed, which are geochemically and by age related to these complexes. Adriatic complex nearby, 70 million years old, dunites, relies everything as it should be. And volcanic and intrusive phases are in the tectonic contact. So we studied both. Just a few pictures how it looks like. These are picrites, but super high magnesium. Actually, it accumulates in lavas. These large crystals are partially altered olivines. Well, I don't know where the scale it disappeared, but some of these crystals were like 3-4 centimeters in size, some much smaller. The rocks had up to 35% MgO, so apparently volcanic accumulates. But we studied melt inclusions in the whole range of minerals and tried to reconstruct the composition of parental melt. This is example we found a dunite otolith, but it wasn't like dunite which you find in traumatic complexes, coarse grained rock. It was very fine grained dunite with preserved melt inclusions in olivines. Now this is how they looked before quenching. So CPX, glass, very fresh and stuff in spite of being 70 million years old. We conducted, not me actually, master student who was in field with us conducted this work. So first of all, they estimated the lower temperature limit for the formation of host minerals. They heated inclusions to the temperature which exceed this lower limit to quench it and get the composition. And then, of course, you need to adjust the composition of the inclusion to the host olivine because they exchange, especially iron and magnesium during cooling. And so this is the composition of, correction of iron set. And the calculation of the inclusion. So this is the adjusted inclusion. What we can see is picritic melt, high magnesium, high calcium, and actually it is also shishanitic, high potassium and sodium. Which from my point of view quite well proves that the empiric model should not be the case. We can explain these complexes quite well by using available arc melts. So now we come to chromatites. As I said, chromatites are quite different. You have not anything like your UG2, like UG1. First of all, chromatites are located exclusively in dunites. You don't see chromatites in norites, in gabbros, in pyroxenites. Chromatites in these complexes, with 0 exceptions, are located in dunites. They are much smaller. They have different composition of prominent spinel. Oh, you can see, by the way, very rare, I think, such fresh olivine for island arc related complexes. Sometimes chromatites are very small. So this is like a series of veins, each not wider than 1 millimeter. But what is interesting, the size of PGM, which you find, are not directly connected to the size of chromatite. Like they can be very rich in PGM. Well, this is example, like this part of chromatite, which was like maybe 5 millimeters in size. And here you can see platinum occupying like maybe 10% of its chromatite. Huge as a ferroplatinum plus platinum iron aggregate. Some other cases you can see lickmanite and laurite. These are normally the only sulfides you can meet, sulfides of ruthenium and osmium. You can see some other intermetallic phases, but mostly osmium, iridium, alloys. And this is very characteristic for Alaskan type intrusions. You don't see much sulfides. You see platinum group minerals related to chromatites. This is redistribution, right? What we saw, what I was showing you, we call primary minerals. Like some people think they're magmatic, some not magmatic, but most people agree that they were the first one. There are minerals who apparently represent alteration of platinum group minerals. So you can see, for example, these rims of isoferroplatinum intergrowing with chloride, different texturally, different compositionally. You see more iron and copper-rich minerals. You can see isoferroplatinum forming crystals in serpentine and chloride. These are all examples of PGM redistribution during post-magmatic processes. For example, here on the left, it's very elegant. You see fracture filled with serpentine and its walls covered with platinum iron alloy. So this is a flat section, but if you think about it in 3D, more certainly it will be something like a channel with walls covered with PGMs. And you also see that in fractures, platinum iron alloys create these beautiful euhedral crystals growing in a fashion like, you know, your pyrite grows in some hydrothermal way, and there is some space. And the last thing is quite interesting, showing PGM ability. You can see this is the thing I'm working currently. You can see these things were osmium alloys. And you can see the relics inside. But now they're substituted to iridium oxide. It's quite interesting because we found that all the osmium from the samples left the system. And what we are left with is purely iridium oxide mixed with metallic platinum and other PGMs. It's, by the way, makes sense. We plotted some charts about activities of these elements, and what we found is if we will progressively oxidize the system at the same temperature, first we will lose osmium as osmium of 4, which is highly volatile phase, and then we get iridium oxide. So general crystallization segments, you have native osmium and laurite, then platinum iron alloys, lickmanite, and then very diverse range of minerals related to serpentinization and other secondary processes. Sometimes I think they're just fascinating. Whatever you can do with this in sense of explanation. So now we came to a mass balance problem. I several times said to you that platinum can be very highly concentrated even in small chromatites. And we can see, for example, in basalts, we have 5 parts per billion of platinum. It actually can be found as small inclusions in chromium spinels in basalts. We recently made work about fractionation of these elements in sulfide unsaturated systems. In chromatites, in regular ones, we have 5 parts per million. This is in chromatite itself, like without DNA. Sometimes it's much higher. So this is order of magnitude, 3 orders of magnitude higher. In some samples, you have percents of platinum. And in the largest nuggets known, so this one, several kilograms, you have more than 90% platinum. So how does this happen? Like when we have sulfide systems, we know that if the R factor is high, sulfide very efficiently extract PG from melt, it can be highly enriched. But how do we do this without sulfide? Actually, there is no answer, but we tried to study these platinum group minerals, and you have some clues. So first, I made a calculations. To form 10 milligrams of ferroplatinum nugget, which is just less than 1 millimeter size grain, you need 1 cubic meter of standard acritic basalt melt. 10 milligrams of native osmium requires almost 20 cubic meters of melt. The largest ever found nugget of native osmium requires more than 100,000 cubic meters of melt, and the largest ever found nugget of platinum requires more than cubic million of meters of melt. So you can imagine, like platinum is very dense. 9 kilograms will be a little bit bigger than this ball. You need to pass 1 million cubic meters of melt through this size, and for some reason, extract platinum? I think the answer is quite clear. They are non-magmatic. Like there is magmatic platinum, but large nuggets, there's no way. So let's begin with the small ones, the ones which are magmatic. So these are inclusions in chromium spinel from volcanic rock. How do we know it's magmatic? This is volcanic rock. This is lavas which I showed to you, which have glassy melt inclusions. You have the same minerals, which I showed you, just much smaller. 200 nanometers, you have osmium alloy, you have platinum-free iron. And they're actually quite abundant. We found visible in the CM inclusions in 1 in every 1,000 chromite grains, and you should understand that this is a small section. This means there are much more of them. Then we employed laser ablation, just drilling holes to see the platinum spikes. And actually we have 1 micro inclusion per 7 laser beats. So all these chromium spinel crystals in volcanic rocks, they're just impregnated with nanometer scale platinum nuggets. Yeah, so these are the trends, how they fractionate and evolve in case of volcanic rocks. And you can see that system works different for different PGEs. For osmium, for iridium, and for ruthenium, and for rhodium, it is 100% controlled by chromium spinel. So correlation is very good. This just means that chromium spinels are the main and probably the only concentrator of these elements. Story is different for platinum. You see this red dot is the bulk composition calculated on the basis of our analysis of chromium spinel grains. You see it explains less than half of all platinum content, because if you continue this trend line, it will be on top of it. This results of platinum being much more susceptible to the nugget effect, much more prone to form large nuggets, and as a result being distributed much less equally. So I told you we can speak about melt composition by studying melt inclusion in chromium spinel, in olivine. But what was quite interesting that we found inclusions in platinum, in isoferroplatinum. And like I was looking for this inclusion when I just began my PhD, and I was thinking, probably we will find, this is chromitite. It's located in ultramafic rock, fresh dunite, forsterite 91. Near chromitites, it can be forsterite 95 sometimes. 89 is the minimum. What do you expect? You will expect to find inclusion of forsterite, maybe some dioxide, maybe some other, so how to say, highly mafic minerals. But what you find actually is feldspar, albite, vargasite, muscovite, and even quartz. Now I want to emphasize, it is in a lot sample. So you take a piece of dunite of chromium spinel, and you get minerals inside platinum, which are not in equilibrium with surrounding rock. So the story was, when platinum captured them, things were completely different compared to these fresh and out of rocks we see now. Okay, maybe this was the unique case. Then we went to epiphytic iridites. This is Adamsville complex in Tasmania. Now these are grains from placer. We studied them, and what we see here quartz, hornblende, enstatite, anorthite. Some inclusions are altered, you see chlorite and serpentine. Some have primary minerals. And what is interesting, their compositions are highly variable. Initially, these things were described in 1991 as benignitic melt inclusions. And the conclusion was that osmium nuggets directly crystallize in benignitic melts. But it just doesn't comply with quartz being present in a major phase in the majority of the inclusion, and also in their high spread of composition. The last thing which we found is actually some of the minerals are apparently metamorphic, because you have such things as anthophyllite or anorthite plus hornblende assemblage, clearly non-magmatic. But this could be a result of later metamorphism. So we conducted, before I go to the model, the last example, this is from Kandur complex, and this unfortunately not my samples. You see these beautiful integrals of chromium dioxide with isoferroplatinum. So all this silver thing is platinum iron alloys. These are probably the most fantastic samples I ever seen in sense of PGM. And once again, how can you explain them forming a regular magmatic process? No, I think there is no way. So we tried to come up with models for these inclusions. trying to encompass several facts we have. First of all, the complexes themselves are magmatic. Like, I don't see opportunity to deny it, like they are connected with volcanic rocks of similar composition, similar age. We see some small PGMs in these volcanic rocks. How do we come from micrometer, nanometer scale alloy inclusions to large nuggets? We invoked multi-stage model. On the first stage, we have early magmatic stage when these minerals directly crystallize from melt and accumulate mostly inside chromium spinner. The second stage implies recrystallization and liberation of these minerals from chromium spinner. At this point, I think, just as stipulation, sulfide should have played significant role, as a sulfide have two nice properties for models. First, it is very good in collecting PGs, and second, you can very easily explain how it disappears, because you can easily dissolve sulfur in oxidized conditions, and you will just have the metallic faces in residues, it is known. Then we suggest that in case of a thalytic, we can suggest several stages of retrograde and prograde metamorphism. This was developed for Adamson in Tasmania, and there are geological reasons to accept it. What we see now is results, is these osmium nuggets with inclusions representing multiple previous stages, which were re-equilibrated at the last metamorphic conditions. In this case, it would be lower amphibolite. And this is the difference for disagreement between phases of the inclusion and the host rock. This is a very, like roadmap, like model, which requires, how to say, very concrete explanations in every single case. So let's bring a little bit summary. Ural-Alaskan types intrusions represent a distinct class confined to island arcs, sometimes to platforms, in case of Alban type, which shouldn't be, sorry.
Just while you're wondering.
Okay. Yeah, which shouldn't be confused with other type of complexes. And they form throughout multiple injections, crystal accumulation, and melt-rocks interaction from high magnesium hydrous and oxidized arc melts. In my personal view, Alaskan type intrusions often overlooked in subduction zone geochemistry and petrology studies. I think they are crucial for understanding the subduction zones, and you will find that works where they are studied not as source of minerals, but as a petrological phenomenon are almost absent. And I'm not saying that I made some of this works. I was almost entirely focused on mineralization. I think it would be really nice if some, like hardcore petrologists will spend time investigating them. And the initial PGA enrichment occurs throughout the magmatic processes, but the formation of large nuggets, especially when they're speaking about the scale of grams, tens of grams, and kilograms, requires multi-stage and not entirely magmatic process. So I want to thank multiple people who worked with me, my past advisors, and my colleagues who have been in field who contributed to this work. And thank you for your attention.
Cool. Thanks, Anton, for the talk. Do you have any questions from our audience in the room? Yes, Grant's go first. Oh, yes.
Thank you, Anton. This is fantastic and takes me back to when I did honors on Alaskan Uralian intrusions. My question relates right to the beginning of your talk, where you spoke about their restriction to the Phanerozoic, and it then links back to your summary where you say they have really important implications for geodynamics, right? So why do you think that they are restricted to the Phanerozoic and not the Proterozoic? And presumably we had similar arcs, or maybe you think differently.
Yeah, thank you very much. So one explanation I had in a paper of, by the way, this paper is cited, Frontiers 2014. They were conducting some experiments to explain why, in some sense, melt will create some seal-like objects and why funnel-like. And I cannot give you all the details, but it related to the rheology of the lower crust. I've forgotten to mention, like, most likely this lower crust, or, like in between of lower and upper crust complexes. And so the thing is that they explained that you require the thermal regime and rheology, which was achieved only in Phanerozoic to get these type of shapes.
Could also be that maybe only in the Phanerozoic do you have wet arc magmas. Maybe the Proterozoic was different and had drier magmas. Might be controversial though.
Yes, maybe. I'm not sure. Like, you think Proterozoic magmas were dry? Mm-hmm. Mm-hmm. No. Okay. That's very interesting idea. I think you like.
Yeah, I was just going to add, is it maybe related also to the redox conditions?
Excuse me?
Maybe it's also related to the redox conditions, so that now because you said that it forms in high Mg oxidized subduction zone. So maybe the redox conditions over time has also changed, become more oxidized, potentially to do with the temperature in the slab and the angle of subduction. Maybe that has a role to play.
Yes, thank you. I think redox conditions are crucial in sense of mineralization, in sense of how, for example, chromium accumulates some metals. There was a recent work about Polaris intrusion in British Columbia. It has exactly the same chromatites, but with no platinum, and platinum mineralization in pyroxenites. They explained it that conditions were so oxidized that platinum, solubility in the melt line wasn't crossed during formation of chromatites and dunite. So osmium iridium precipitated with chromatites, platinum remained in melt, and that formed mineralization in more evolved rocks. So in this sense, I think redox conditions are very important, but I'm not sure, I don't know how can it influence the emergency appearance of zoned dunitic complexes. How is it direct? Like maybe there is connection, I just cannot think about something as direct as what Grant meant about hydrous melts.
Lou Ashwell is online and has his hand up. Lou, do you want to ask your question? You need to unmute yourself.
Yeah, I'm here. I was hoping that Grant would explain a little bit more about his honors work, which was
just hold there, Lou. We just need to increase the volume in the room.
No pressure, Karen, no pressure.
Doesn't have a PhD in AV. Try again, Lou, please.
Can you hear me?
Oh, yeah.
All right. So I think it was 2010, and Grant Bybee did his honors with me on some ultramafic bodies in Madagascar. And I think, or he showed that these are probably some of these types that you're talking about, these Alaskan zoned bodies. But the main thing that was an outcome of this work was negative ruthenium anomalies. So I was hoping that you would plot platinum group element patterns. I guess you normalize them to primitive mantle or something, and there was a connection between negative ruthenium anomalies and these Alaskan type bodies, and also the subduction environment. So I don't know if you're aware of this work, but maybe you want to look into it. I think it was published in EPSL, and Grant can tell you a lot more about it because I think he's sitting there and I'm not.
Do you also see negative ruthenium?
Yeah, thank you very much. I also have a paper when we discussed it, and actually several works about Kamchatka. This is very typical thing. And like this is as typical for our croxons, like negative niobium tantan anomaly on trace element patterns. There were two explanations, quite related. So first explanation is, I made it in 2021 paper, but it's not, like my invention. I was based on the work of John Wopak, is that due to oxidized conditions, in this work of Park 2017, they showed that for ruthenium, dependence of its, affinity to chromium spinel from iron 3+ content is stronger than for other elements. So when you have more oxidized condition, ruthenium all these elements, they increase their partition coefficients in chromium spinel, but ruthenium is the fastest. This is first explanation. Several explanations. Second thing is that there is mineral called laurite, and this is the only sulfide which is stable in sulfur under saturated conditions. There's work by Bokrath and Ballhaus, 2002. You can crystallize laurite, ruthenium S2 from sulfide under saturated melt. And in the same principle, it can be retained in the mantle during mantle melting when, due to oxidized conditions in arc settings, all sulfides are being destroyed, PG is dissolved, but laurite can stay and, how to say, like retain this ruthenium. So thank you. And to my shame, I am not aware about this Madagascar paper, and I will read it because I know this complex, Manampotsi River. There was paper by Louis Cabri. They described this iridium oxide, which I showed you for the first time, was described in Madagascar in 1992 in Placer. Thank you.
We have another hand up online. I can't see the name. I can only see a. Oh, it's Race. 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 Go ahead. Ask your question, please.
Yeah. Thank you, Anton, for a very interesting presentation. Anton, can you please repeat what is your, maybe I missed, what is your preferred interpretation of this reverse chemical zonation of the Ural-Alaska-Type complexes?
Thank you for the question. I will open one of the charts version. I do not understand why they reverse, because you see you have ultramafic rocks in center and more evolved rocks to the boundaries. So if we imagine this sort of scenario, it doesn't look reverse. And once again, I said imagine. This is not, I'm sure that this is true, but if you look at this, we will have dunite in the lower part. So I don't exactly understand why is it reversed. Could you please clarify? Thank you.
Yeah, it's usually referred as reverse because, you know, the bodies, they are these are at least the ones which I studied myself in Alaska. They are pipe-like bodies, and cooling takes place from the margins. So that's where crystallization takes place. So if we go from the margin inwards, then we'll go from olivine gabbro through pyroxenites, verlite, and then dunite. So that's why usually it's referred as reverse.
Oh, thank you. Yeah, now I understand. Now I understand. 1 second, I'll open the slide. I talked about it. Explanation. Yeah. So I mean, explanation. These were experiments by Hattaji in 1960s, work by Murray. Explanation is that you have a flow differentiation in these tubular channels, and as I said, this is quite counterintuitive. But if the system exists for a long time and you have some melts of crystal cargo, then at a certain point you may have heavy phases being accumulated in the central part, and this is for me highly counterintuitive. But there were experiments. This is one of the explanation. Second thing, I also want to emphasize that dunites, as we see them now, are highly changed rocks. I don't want to say metamorphosed because metamorphism is a little bit different thing, but many times recrystallized and changed under influence of later rocks. I showed you the small dunite veins in pyroxenites, which my preferable explanation formed through infiltration of melt through mush, which dissolved more soluble in melt minerals, destroyed pyroxenes, and left intact refractory olivines. So what if the whole dunite course of these complexes are in some sense these melt mush, melt rock interaction products, not primary accumulates? And we don't have primary accumulate textures, but some highly metamorphosed recrystallized unit. So if we combine the first thought about flow differentiation with this second idea, maybe it gives us some sort of broad picture about how this reverse zoning formed. But this is not, you know, just simple crystallization from margins to center, because you are right, like we wouldn't get anything like this in this sort of scenario. Thank you.
Thank you.
Maybe I can ask a quick question. So on your whole enrichment in terms of the platinum nuggets depends on metamorphism. Do you see evidence of metamorphic textures in the dunites, in the clinopyroxenites? Is there evidence of metamorphic events in the surrounding country rocks, which corroborates that metamorphic overprint?
Thank you very much. As I said, like very accurate with what metamorphism, because I meant recrystallized and changed by influence of later melts. It's not necessarily regional metamorphism. But for example, in case of these rocks from Adams Field, and I want to emphasize they are not Alaskan type, they are phyalitic, but I just put them due to them being interesting. They have these minerals like antophyllite and other interesting things. They are located in metamorphosed complexes, in Ural Mountains also. But the ones I studied in Kamchatka, no, country rocks are not metamorphosed, maybe metamorphosed in prehnite pompilite phases. When I say metamorphism, I mean recrystallization, and we have evidence of it. I unfortunately didn't put the photos of thin sections, but we have perfectly, I forget the name of texture, how do you call it? Like, yeah, granoblastic. You have perfectly granoblastic dunites, which actually, as our petrography professor when I was a student told, if it wasn't olivine, I would say it is a quartzite. Because like, if you forget that this has olivine birefringence, it looks like a quartzite, completely recrystallized rock with 120 degrees between crystals, and this is very typical for dunites. There are interesting things which happen between for example, dunites and pyroxenites. No, I have many pictures that just wasn't prepared to put it all here. Yeah, I mean, this is my favorite. It's just like secondary dunites and mineralites and pyroxenites, but this is what I think melt rock or melt marsh interaction. Dunites directly never interact with country rock. It's quite interesting. Never, like they only interact with mineralites and pyroxenites and gabbros, and there is no serious evidence of in situ contamination in this like.
Thanks very much, Anton, for the
Thank
talk.
you.
Thanks everyone for joining. And nice talk.
Yeah, thank you.
We'll see if Grant and Karen join. I'm just going to stay for one because I need to tomorrow. Lou sent this paper, this Madagascar paper.